This is the Nelune and TCRN Randwick Roundtable, and I'm delighted to introduce Professor David Goldstein. I would predict that this is the first time a physicist has spoken at this roundtable, and certainly the most eminent one we've yet had the opportunity, but I'm sure there'll be more as time goes on. So Iwa and I share a Polish heritage, but apart from that we share nothing. She's far too smart for me. But she's the Deputy Director of the ARC Centre of Excellence in Nanoscale Biophotonics, but most importantly a trained physicist and the Sharp Professor at the Graduate School of Biomedical Engineering. She's a Fellow of a variety of societies, and most importantly was the winner of the Eureka Prize for innovative use of technology in 2016. So she's really going to give us a very interesting, in our usual fashion, 5 different concepts that she's going to introduce to you to give you some background and really a very, very interesting look into the future.
Hi, thank you so much, David, for inviting me over. It's a real pleasure to be here. When David first invited me to speak at this forum, he gave me a list of bullet points I'm supposed to be addressing. So one of the bullet points is, what on earth is the physicist doing here? And I was trying to find this concise answer to this question. And the best answer I could come up with is that I am really here to try to bridge the gap. And it just happens, and I didn't know that before, that bridging the gap is the main part of the logo of the Translational Cancer Research Network. So it is very, very fortunate for me to be here and to be part of this network. So I will tell you a little bit how it came about that I am standing in front of you here. That was really precipitated by health scare in my life. So early in my life, around year 2000, here me with bushy tails and hairstyles all directions, I went to the doctor and they said, maybe you've got this type 2 diabetes, maybe we need to test you, and then they prescribed a kid's test. And I went to the doctor and then they drew blood from me, that much blood, and then I had to wait in the doctor's office for 2 hours, drank this ungodly mixture of sugar and water, and then they tested me again. And at the same time, I was reading some papers on my laptop, and there were papers about single molecule detection. Now, what they were doing in this test, they were testing the level of my insulin. And here I am reading about those single molecules and how it is possible that people can detect single molecules, and I have to give that much blood for this test. Now, what this was a translational gap, and I realized that there is so many of those gaps, and maybe, just maybe, with my skills, I can start addressing them one by one. And I've been addressing them ever since. So here is me in various stages of my life. And here are some gaps that I was trying to address, still addressing those. That's one of my projects going very soon. And sometimes we've been doing some more courageous little jumps over some translational gaps. And that basically was the story of my life over the last 18 years or so. Now, in the meanwhile, I had to sacrifice my body to science. This is me doing experiments. So here is my blood draw. I've been a subject for a motor neuron disease study that I cannot tell you about because it's not cancer. And here is me. We rejigged an ophthalmology equipment to be able to see things in ultraviolet, and then I spent 3 months trying to calculate how much can I safely put on somebody else's eye, and then I realized that only me can give informed consent because this was such a complex calculation, so I gave myself informed consent and I tested it on my own eye. And that is within the framework of NHMRC ethical research conduct. So I've been doing all of this, and another translational gap that we've been made aware of and that we've been trying to bridge was the gap between research, the lab, and the industry. So we've been trying to bridge that with my colleagues, some of whom are here, setting up a little company that I might chat to you about later. Now, a significant event in that period was the setting up of the Australian Centre of Excellence for Nanoscale Biophotonics, where I am Deputy Director. It is a big organization. It has attracted over $40 million from Australian Research Council. And at some point we counted how much money we have leveraged, and that was actually 155 million. So right now I can't tell you because it was very quite complex to calculate all of this. But no wonder, there is plenty of us here and a lot of different research partners and industry partners. The remit of the Center of Excellence is looking at sensing and imaging that takes information from the nanoscale level, from the molecular level, and takes it out to the organism level. And it is quite difficult to bridge that gap, and we need new tools. And our emphasis was on tools that can be deployed in vivo, tools that can be deployed in real time, that are able to follow what is happening in cells, in tissue, and real time. And finally, building on the skills that we have as physicists, chemists, and engineers, and biologists, we would like to engineer devices that are deployable and they will be able to work at the point of care. Now, I don't have all of those in those slides because they told me 5 slides per point, so any of that I am perfectly happy to cover off in some later talks. But that basically is the big picture of what we are trying to do. Our Center of Excellence does not have cancer as the main focus. The focus is neuroscience, cardiovascular disease, and also reproductive science. But because we are coming to the end of our funding period, we are now looking at transitioning our technology and deploying them for cancer. And this is why I am here, to understand, to sort of get familiarized with this community, perhaps present what we can offer, and also explain what are the deliverables that a physicist can bring to the area such as this. And they are represented in the points that we will be discussing in a moment.
Okay, so any questions about that process? How a physicist becomes a biologist? Okay, what about, is there some tipping point, some particular event? You mentioned it was a health scare, but something else where you said, my background and my understanding of physics is going to be important and can add something to understanding biology?
Well, I think there is historical evidence that physics has contributed to life sciences. An example is the development of magnetic resonance machines and also PET machines. Now, they have physical principles behind them. And in fact, the MRI machine was developed by one of my professional colleagues who also worked on autofluorescence of cells and tissues. And of course, those machines, they start their life as some ideas, and they are not really applicable to proper medical situations. But then, as they mature and the technologies are taken up by the industries, the sophistication grows, and also the applicability of those technologies grows. So I think the physics provides the nucleus for change, and that's hopefully what we can deliver to the community.
David, I find your amazement at the involvement of physics and medicine quite extraordinary because, of course,
Physics and biology.
Physics and biology, well, Richard Feynman, I don't know if you know Richard Feynman, yes. Nobel Prize winner. Yes. He used to spend his spare time working at the biology labs on his sabbatical. So there is a very long-term, close association.
Can I just follow that up? I'd be interested in your thoughts on Erwin Schrodinger's argument that biology is no more than physics and chemistry, organised in time and space.
Well, I don't think that you are going to be able to draw me properly into this debate, but what I will be addressing this a little bit. Obviously, there is a significant stepping up in the level of complexity. As you go from physics to chemistry to biology and to medicine, and then to population level behaviors, the complexity grows and grows and grows. And tools that physics have developed are not necessarily best for dealing with complexity, but I will address that particular point a bit later.
It's a great teaser to start the next part.
Okay, so the first thing is what actually can physics bring to the area of biology and medicine. And one of them is that we are able to develop new tools. What kind of tools? Well, all sorts of tools. And here is an example of a fantastic illustration from somebody who has a name DeviantArt. It's a thing that goes into your body, has all sorts of lasers on it and all those things to be able to move them. So all those fantastic ideas, in principle, could be realized. And this is as opposed to the standard instrumentarium that everyone else has. Now, in reality, it is not quite like this. In reality, the tools that we are developing are rather like this, a little bit. And you know, this is not really going to work, but maybe it will work in the future. And so I would like to show you an example how we develop those tools. And now why do we need those tools? Well, because medicine in the past was looking like this. Everyone was supposed to undergo the exact same treatment. And so that was 19th century medicine. In 1950s, there was a new sort of significant change. We realized that there are genes in the cells. And those genes can perhaps inform the treatment, so genetically sort of motivated treatments. Now we start to understand that that is not the entire story, that there is something a little bit more deeper going on behind the genes, that there is epigenetics, there is transcriptomics, there is this, there is that, which means that there is something missing in this picture. So in order to understand what else needs to be brought to understand and treat disease, we came up with the idea of maybe there is something to do with the different dimensions. So number one, space is important. You want to understand where is the disease in the body. And because I am a physicist and I had a primitive understanding of medicine, to me it was obvious. But, for example, in the case of pain, that is by no means not obvious. Where is the pain located? Is it here, or is it here, or is it here? Who knows? So we want to be able to understand and probe the disease locally and where it happens. We also want to understand the time course of the disease. Now, many of the technologies that we have for biomedical and biological probing are not really very well suitable to time courses. And then, on top of that, there is the characteristics of the individual. Now, I mentioned genes, but now we have a different question. Genes, but whose genes? My genes or my microbiome genes? Whose genes we are talking about? All those are unsolved questions. So in order to be able to address this multiplexing in signals and mediators, we need new tools. And so I will tell you a little bit how we have integrated this time and space into sensing. And yeah, I know this is a fun-looking slide, but it is really very simple. Our aspiration was this. We would like to have a little mouse that we are using to understand some neuroscience phenomena, and we want to be able to probe cytokines in that mouse over a period of, let's say, 8 hours. Now, a mouse is a very, very small animal. You cannot really use standard methodologies to do a longitudinal study of a mouse. So what can we do? Well, we thought that, so these are our targets. We want to sense some cytokines. Cytokines are molecules that are pivotal in the functioning of the immune system. And they are called signaling molecules. They are present at a very, very low level, 1 picomolar. In plain language, that translates to extremely low. Sensing volume, that poor mouse is tiny, and I would like to take it from the tail. So tiny little volumes, how do we do it? Standard methodology to detect cytokines is ELISA. It's ELISA assay, needs 10 microliters. What can we do? What we have done is we thought, okay, there is optical fiber. You are all familiar with optical fibers. You have them sort of under the pavement here. It takes signals to your home or close to your home. And it is a well-established technology and incidentally made of glass. Glass is actually a good object to put assays on. So what we have done is we decided to put ELISA assays on those optical fibers instead of a glass slide. And that's how they look like. These are pieces of standard telecommunication optical fiber, and on this optical fiber we have the assay. And it is, for those of you who are familiar, it is a standard salvage immunoassay. Antibody goes on the fiber, detects cytokines, then we take out the fiber and then expose it to another antibody with some label, and that label is a nanoparticle. And so when this assay has worked and we have labeled it, this is how the fiber looks like. It has some fluorescent on it. That's the signal indicating the presence of cytokines. And if you have a lot of cytokines, there is a lot of signal. Not so much cytokines, not a lot of signals. Now that apparently is a discovery, a patentable discovery. I didn't know that. We just thought, okay, let's just put it on the optical fiber. And we put it in a cannula, which we needed to perforate, and because we know laser technology, we perforated those plastic cannulas very nicely. And so that was published, and we then thought, okay, we need to put it in some in vivo situation. Now, because we collaborate with neuroscientists, we thought, okay, let's do a neuroscience experiment, because in a neuroscience experiment, putting cannula in animals' head is standard practice. So a cannula is shown here. It's a little device that goes into the brain, and you can see that thing here on the cross-section of the brain. This is the place where the cannula was. And it is implanted chronically, and you can put things in and take things out. So this is how the experiment works. We have stimulated the brain with LPS, which stimulates the production of a cytokine. In this case, we've been looking at IL-6. Then we put the fiber in, incubated for a couple of minutes, took it out, and then measured the cytokine. And here is the result, that 1 hour after stimulation with LPS, the cytokine level goes up, and eventually everything calms down and the cytokine level goes down. That's the first ever observation of cytokines in the living organism. And then we thought, okay, well, let's do something a little bit more adventurous. But that required a re-engineering, because we wanted to put this to understand cytokine secretion in the spinal cord. Now, spinal cord anatomically is much more challenging, and I understand that there might be surgeons here in the audience. So I put here a surgical picture, so to convince you that yes, we can do surgery in our team. Intrathecal space is a space somewhere along the spine here, and you can put a catheter in. But that catheter goes like this. It goes in between the vertebra, and then has to make a bend and goes into the spinal cord. Now, you cannot do this with the glass. Glass doesn't tolerate that. But we can put that on a piece of wire. So we quickly purchased some steel wires. Then there was a requirement for a little bit more chemistry to be able to put this assay on. But here is the steel wire, and it is able to detect cytokines by the exact same principle. And here is the result. This is in vivo cytokine secretion in a chronic pain model. So we have rats that have been prepared to experience chronic pain. This is the amount of allodynia that they experience by day 14. And we can show that as the days go by and the chronic pain becomes more and more unbearable, then the cytokine levels goes up. That's unpublished data. But it illustrates that we are indeed able to take the measurement right where it needs to be into the body. And I think that's my little intermission. We have done something else, control of drug delivery of space and time. I will chat about it maybe after we
Yes, so we'll come to that next. So, some thoughts from the audience about any thinking about this technology and how it would help solve a particular cancer problem. So maybe I'll start by talking about therapeutics and looking at how you think such technology might influence pharmacology, pharmacokinetics, understanding about drugs.
Thank you for this question. I think this is actually a very deep question that probably deserves to be taken to a workshop setting, but I can try to sort of give you my understanding. Cytokines reflect the response of the immune system to anything that is happening. If the immune system is interfered with, let's say in a beneficial way, by trying to make it more aggressive against cancer, that could have influence on the cytokine level. And if that cytokine level can be probed locally, near the site where everything is happening, then this is a capability that could support drug development.
Okay. That stimulated some people. Let's start at the back.
I have a question about, can you interpret the position of the signaling at different positions along the length of the steel or the glass? Could you insert it into a tumour, for example, and look at different positions, depths within it, in terms of where activity is happening?
Absolutely. This is shown here. So that's plot that has a spike shows the response of our steel wire to an injection of LTS in a particular location along the spinal cord. And on the horizontal axis is the length in centimeters. So you can see that at around 8 to 8.5 centimeters from some reference point, we had an increased amount of IL-6, and at 7 we had basically the baseline level, which means that this particular fiber, the spatial resolution was in the order of 1 centimeter. But this is because we injected and it diffused away. Now, in experiments in vitro in the lab, we have the resolution of few hundred micrometers. So yes, you can actually take the quantification to the source with spatial resolution that has never been possible before. Standard measurement of cytokines is from blood, and that integrates everything that is happening in the body.
Yeah. So Ivan, you might use a PET scan to tell you within 24 hours about the effect of a drug, and in different metastases in different parts of the body. What would this technology add?
I think one of the challenges that we have in looking at human translation is scale. So this tends to be very fine scale within a lesion, whereas I think it may be difficult to do whole body and multiple lesions, but I think being able to span across all of those dimensions would be absolutely fantastic. I think one of the other things that we have is that our method of doing dynamic assessment is through the serial studies. But if you have, and I may not be quite understanding the science correctly, but if I understand it, you have to put in a series of probes and then each time point pull out one to get a readout. Is that correct?
Yes, this is correct because in this particular implementation, we used a sandwich immunoassay. However, there are chemical sensors that are able to carry out real-time sensing, and they are based on shape-switchable molecules. Now, this is the technology that we are working on with Dr. Buozhen Liu, who is a future fellow. It is an aptamer-based technology, and we are absolutely aware that real-time sensing is the holy grail, but chemically it is not that straightforward. I think there is a trajectory how to achieve it, but I wouldn't say that we are demonstrating this yet. We can reproduce them, we can show reproducible, repeatable measurements, but not the actual time. The other question that is sort of really similar to this is, okay, so can you actually get away with taking out the probe? Because taking out a probe from the intrathecal space, that looks like a really bad procedure. Let's put it in there and have it in there for a long period of time and just take readings from the end. Now, that regrettably needs big gun physics. There is an approach which we think we could employ. It involves sophisticated pulsed lasers, and we haven't achieved this yet. So we are working on it. It hopefully will happen. It will be revolutionary.
So Professor Goldstein is available afterwards, so in the interest of getting through the next bit of excitement, we might stop questions there.
Thank you, David. So I've been speaking to you about development of new tools and gave you examples of some tools, but now I would like to switch gears, and I will skip this one. Physics is also an area which thrives on models. Now, what is a model? Well, let's take a brain. This is with the whole complexity. We don't know what is happening, but maybe, just maybe, we can create more simplified versions that are obviously not capturing full complexities, but they are sort of useful. They render some features of the brain, and they don't have a sort of a whole hierarchy of models. The models that we are working with in our laboratories are models that potentially fill the gap between standard testing of drugs in conventional cell cultures and animal testing. So everyone who works with animals would know animal testing is challenging. There is ethics, there is the accuracy, how good is that model, and there is the time that it all takes, and also the cost. Now, obviously, ethics is becoming more and more concerning. Reproducibility is also an issue. And then there is the added complexity that are animal models actually a good models for humans. So all of that are valid questions, and we are not going to solve them, but what we are trying to do is to put something in between planar cultures and animals, so that there is at least an option to eliminate choices that are completely not going to go anywhere. And so with Anna Guller, who is here in the audience, our team is developing multiple types of three-dimensional structures on which you can see the cells. And this is how they look like. They start from whole organs. Those organs actually come from Woolworth here in Randwick. We buy them, and I swear, on Monday I bought 300 grams of chicken liver and put them in a machine that removes the cells. That machine sort of resembles a washing machine, and in a month's time we are going to have this. The cells will be completely removed, and all that would be left would be a collagen structure that holds the organs together. And not only it has collagen, it also has the factors that actually encourage the growth of cells. And so that's how they look like in cross-section, and we can see the cells on them. We can cut them into pieces and put them in 96-well plates to have replicates of something that sort of looks like tissue. And Anna, who is shown here, has done quite significant amount of work trying to see how cells grow on such structures and how they can form what we believe are early stages of metastasis. So you can see here on the left, this is a histology image of one of those pieces of that scaffold with cells which are triple negative breast cancer cells, and they were seated on this structure and allowed to invade. Now, surprising fact is that we actually grow them for over a month. That culture is very happy growing. This model has a number of very spectacular features. In particular, it is very easy to show the effectiveness of drugs changes significantly. Here are some data on IC50 of doxorubicin in standard and nanoparticle format. The comparison with two-dimensional structures is incomparable. And you can really clearly see why it is much harder to treat a three-dimensional structure. Those constructs are angiogenic, so we demonstrated the angiogenic switch, and here this picture just shows where the doxorubicin is located. So early stages of metastasis, it's obviously a scientific study only, it's not a translational study. But perhaps a little bit more translational is the current study that Anna is leading, where she's trying to develop models of brain tumors. And again, brain starts its life in a shop. We buy it in the shop, and then very carefully decellularize, because the scaffold in the brain is much more subtle. You can see here, it's sort of almost transparent and wispy. But it is a very good scaffold, and it supports the proliferation of cells. For cells, we are using here those two groups of cells, astrocytes from glioblastoma and proneurons, PC12 cells. What happens is that those cells grow extremely well, and this is the data that I have shown at a conference earlier this year. What you can see here are the glioma cells for stained like that assay, and you can see a lot of green cells. What it means, it's sort of like a tissue, and that tissue can be grown for a month. So cells are alive, cells are extremely happy, and not surprising because they are a bad cancer, but they also produce